All right, welcome everyone. Starting on chapter 4 now, I'm going to talk about, we're going to start talking about bonding. So we've talked about electrons and what electrons do and how they're arranged, and now we're going to talk about what they do in reactions, and this is going to lead us to understand how compounds are formed, and which we'll be able to start talking about reactions and things like that. So a couple of definitions I'm just going to dump on you. Now, it's funny, these definitions, I've already talked about the concepts in chapter 3, but I'm just going to put names to it now. So remember how I was talking about how what really dictates the properties of an element are the electrons in its highest energy shell. So if we look at 1s2, 2s2, 2p6, 3s2, 3p2, right? What really matters is that in its highest shell, right, there are 4 electrons. That's what really, really matters. So there's a name for this. The highest energy shell is called the valence shell. That's all that means. The valence shell is the highest energy shell. Right, the outermost occupied shell, or the highest, the one with maybe not even the highest energy necessarily, but the one with the highest n number in front, right? So the outermost, the one that's farthest away, and that's what's important here. So even if you get up to things like, if you look at like argon, 4s2, 3d10, 4p4, right? I still say there's only 6 electrons in the outermost shell, right? So the 3d is technically higher in energy than the 4s, so I'm not really talking about highest energy necessarily, but what happens is the 3ds, though higher in energy, are actually farther in. So when atoms lose electrons, they lose them from here and here first. So it's really, those are the outermost, the ones that are the farthest away from the nucleus. It's a little weird, but what you're just looking for is the highest numbers out in front here. So, valence shell is the outermost occupied shell, the highest shell number with electrons in it. Valence electrons are electrons in that valence shell. Everything else is called a core electron. So these electrons are closer to the nucleus, and so they're kind of inside. If you think about an atom and its electrons as sort of layers on an onion, the valence shell is that outermost layer, and until those are all stripped away, you can't get to the inner one, right? So really what's most critical, and so kind of why we did all of the electron configuration really boils down to kind of one simple thing. What's most critical about identifying an atom's properties is just knowing how many valence electrons it has, just how many, right? And so atoms with the same number of valence electrons will have similar properties. So if you look at, say, chlorine, so if you look, say, at chlorine and bromine, if we look at their noble gas notation, electron configuration, chlorine is neon, (3s2, 3p5). Bromine is argon, 4s2, 3d10, 4p5. Now, if we look at the number of valence electrons each of them has, chlorine has how many valence electrons? It has 7. 5 from here and 2 from here. Bromine has 5 from the 4p and 2 from the 4s, so it has 7. The reason chlorine and bromine have similar properties is because they both have 7 valence electrons. So it's the number of valence electrons that really dictates what an atom does and how it behaves. So, and why do they? Because the atoms So why do valence electrons have such a large impact? It's because the ones on the outside, right, are the ones that encounter other atoms first. The ones that are buried in the middle don't matter that much. Okay, having done all that with electron configurations, it's actually a lot easier than writing out something's entire electron configuration to figure out how many valence electrons it has. We can, and I want you to, I went through that because I want you to see why that is, where all this comes from, but really there's a nice shorthand way to come up with the number of valence electrons. And it actually comes from looking at the periodic table. Now, my periodic table here, which I have momentarily misplaced. Now, my periodic table here doesn't actually have the proper labels up here, so I'm going to have to write them in. Now, I'm going to use the Roman numerals and the A's because they're really much more relevant here. 1A, 2A, 3A, 4A, 5A, 6A, 7A, and then 8A, right? So 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So it turns out that all of the in 1A, their electron configuration always is going to end in NS2. No, I did that wrong. NS1, right? 2A will end in NS2. Now, the N is just saying the value, the number out in front depends on which row you're in, but it'll always be something S1 for this column and something S2 for this column, which means these are always going to have one valence electron. So I'm going to write one valence electron up there. These guys will always have two. Over here in 3A, you'll get one of two possible combinations. You'll get NS2 NP1 or NS2 and minus 1D10 NP1, right? Whether or not there's D's intervening doesn't matter because they aren't the valence shell. They're not in the outermost shell. So we just sort of ignore them for purposes of determining valence electrons. In either case, you're going to end up with 3 valence electrons every time. And likewise, 4, 5, 6, 7, 8. So a couple important things here. One, you can figure out the number of valence electrons an atom in the representative group has by looking at this column number, right? The Roman numeral before the A, that tells you overtly how many valence electrons they have. So anything in group 4A has 4 valence electrons, right? 4 electrons in its outermost shell. 5, 6, 7, 8. Now, you may have heard before, some of you may have taken chemistry before and heard that, you know, electrons fill up as you get 2 in the first shell and then 8. And this is all very true. And then you hear that it goes 8, 8, 8, 8 after that. That's not precisely true because what happens is, right, as you're filling, you go, you know, you have 2. The first shell can only hold 2 electrons. That is true enough. The second shell, oops, I'm going out of order. The second shell can only hold 8 electrons. Also true. But the third shell, right, 3s2, 3p6, and then we go to 4s2, right? Then we go back to 3d10. The third shell can actually hold 18 electrons because of these 3d10s. But this idea of valence electrons being in 8s came about, and it's an important number to remember. But I just want you to know it's not true in every possible sense, right? The reason we get the idea of all shells filling up at 8 is because after 8, that's when the next shell begins. Now, after that point, we may backfill into the third shell, but really, after 8, you start a new shell and then a new shell. You're never going to have more than 8 valence electrons. After 8 valence electrons filling up the S and the P, then you start the next shell at S, right? So that's where we get this idea of 8. 8 is the most valence electrons you could possibly have. So it's really key to understand that, well, the first shell fills up at 2, and then after that, after you have 8, you have to start a new shell. And that represents a lot of energy. There we go. So, as I was saying, you can determine the group, using the group numbers, you can figure out how many valence electrons you have. So, group 1A has 1, 2A has 2, and so on and so forth, all the way up to the noble gases. We are not going to worry about the number of valence electrons a noble gas has, because in a technical sense, they're always going to be 2, because, I said noble gases, sorry. For transition elements, we're going to it's always going to be 2, right? Because you'll always have NS2, and then I keep saying noble gases. A transition metal has its electron configuration stops somewhere in that D block, so it's always going to be N-1 D something, right? But this is actually my number of valence electrons, so it will always be 2. So it's not that useful. For transition metals, we deal with something else, and I'm not really going to go into that. It's not really important for what we need to do. So I'm not going to ask you the number of valence electrons of a transition metal, only a representative element, something in the A groups. So take a moment, and I want you to determine the number of valence electrons and core electrons. If you can't figure out core electrons, sometimes this stumps people, just do the valence electrons for each one, and then I'll talk about it. So pause it and try these. Okay, so carbon is in group 4A, right? Which means it has 4 valence electrons. That's simple enough, easy. Now you may be thinking, what the heck do you mean by core electrons, Steve? I don't understand. So remember, think if you can, or look back at what core electrons are. Core electrons are any electrons that are not valence electrons, right? So all we have to do is figure out how many total electrons carbon has, and if you subtract away the valence electrons, well then you have the core electrons. So how many electrons does carbon have? It has 6 total, 4 of which are valence. The remaining 2 must be core. Selenium is in group 6A, which means it must have 6 valence electrons. It has 34 total electrons, so the remaining 28 must be core, right? Calcium is in group 2A, meaning it has 2 valence electrons, 20 total electrons. The remaining 18 are core. Lithium has 3 electrons. 1 is valence, we know because it's in group 1A. The remaining 2 are core. Krypton is element number 36 with 36 electrons. It's in group 8A. The remaining 28 must be core. You will start seeing, if you do enough of these and try to figure out how many core electrons it has, you'll see the same numbers coming back again and again and again and again. It's always going to be 8, 10, 18, 28, and then I can't remember what the next one is. Doing math real quick in my head. I'm suspicious that it is 44, but I'd have to look. So, anyway, so that is figuring out valence electrons. I'm not going to ask, I may ask you core electrons sometimes, but I want you, if you're having trouble with that, it's not as critical as knowing valence electrons. Being able to figure out how many valence electrons something has is key. Now, I will give you a periodic table on every exam or quiz for you to use. So you can reference this. So there you go.